right. Welcome to this session. We're kind of kicking off the sessions after the keynotes here and starting off with a lot of FHIR content, not only this session but others this afternoon. So what I'm going to talk about is a pipeline that we've developed, really taking data that's in FHIR all the way to IntegratedML, which is in-database machine learning in our InterSystems Iris data platform. So we're going to, I'm going to kind of introduce the problem. We're going to talk about learning healthcare systems and how machine learning might fit into that general concept of population health. And we'll go over the pipeline. And one of the key tools that we used to build this pipeline is called DBT. It's Data Build Tool. It's an open source package. And then at the end of that, we use IntegratedML. So a little bit about what this is about and what it's not. Okay, so I have this slide. It's really like there's a journey, there's a long winding road for when you start with messy data and end up with insights or analytics. Typically, and this is difficult because healthcare and health IT is hard, the data is messy, it's voluminous. And typically, when you're serious, you're going to set up a clinical data warehouse. And we have products for this. We have Health Insight, which is exactly that. OMOP is another standard. It's getting a lot of momentum for a clinical data model. Excuse me? What does OMOP stand for? I can't remember. Open, da-da-da, I don't even remember. Who knows? Pat, do you know? You already stumped the speaker. Okay, thank you very much. Of course, that's Googleable. So anyways, it is an open standard, and it provides a whole bunch of the infrastructure that you need to really handle healthcare data. There's different laboratory reference codes that you need to manage. There's a lot of variability that a complicated data model helps with. That's not what I'm going to be talking about. I just developed a pipeline that does a lot of the same steps, a little bit quick and dirty, but it could be applied to many other types of data, not just healthcare data. So we've used FHIR SQL Builder, which is a technology that we have that allows you to keep data in FHIR repository, but also see it in SQL. We have IntegratedML in the mix, as I mentioned, in database machine learning. That's just very simplified machine learning. And of course, I mentioned this DBT adapter, and we have a community-supported adapter that we've been building up to support this. So a bit about learning health system. So I found this paper, it references learning healthcare system or learning health system. And the idea is that you're continually collecting data. You want to make that data better as you collect it, as you operate your healthcare system, and then feed the insights back into the system, making the system better as you go. So it's kind of this round and round you go. And there was this paper that used synthetic data, which is what I'm starting with, generated by open source Cynthia project. And as you see down the bottom, they just used CSV output. It's a bunch of different tables. They varied the number of patients from 30,000 to 150,000 and showed that as you added data, your models, your machine learning models for lung cancer and stroke prediction, which were just some examples they used, would get better over time and with more data. And they gave a lot of information about how they did the feature extraction, how they used, how they identified the codes they would use, codes being like LOINC codes, SNOMED codes, these types of things that denote what procedure happened or what lab result was collected. And they talk a little bit about their machine learning process and what algorithms they use. So this QR code will take you to that paper. It's open access, and it's pretty interesting, but it's really straightforward in the sense that you're taking data from across the healthcare system, and you're distilling that down for each patient one single set of data and then predict their risk score for whatever condition you want. In this case, I said lung cancer and stroke. So we recreated their pipeline. I actually asked the authors for the pipeline, and they demurred for whatever reason. But they do have a lot of the data available in that paper. So really, the process goes like this. First, you have to get your data from FHIR to SQL. Then you want to take that SQL data, which is still in multiple tables, and you got to join them up into one table, and you have to decide how to take multiple observations, multiple diseases, multiple things, and get it into one row. And then at the end, you're going to do machine learning on that, because that's the type of format that you need to do machine learning. So we start out with our FHIR repository. We get the data into the FHIR repository, InterSystems Iris for Health instance. And then we use the FHIR SQL Builder, which is a feature in that, to just select the data that we want, mostly about these codes that I was talking about, the coded data that's within the FHIR data set. Then you have to do this kind of transformation to get it into ML-ready format. And so you extract all of those lab result values, you normalize them across different units, and then you split up your patients into target and background patients. And then you put that data all back together, pivot and join it. And then once it's pivoted and joined into one format, you can split it into training and test subsets, which is a critical part of machine learning. We do that all within the database. And then run IntegratedML, which you train a model, and then you can use the model, but it's all driven in the pipeline. It's not a manual step involved here at all. So I'll dig in a little bit to each of these. We generated Cynthia data. As I mentioned, we have the FHIR repository, the FHIR SQL Builder. We used all these different tables. And the main thing to note about the FHIR SQL Builder is the data is projected. It's not copied. So within our multi-model InterSystems Iris database, we store things at a lower level representation that can then be projected in different formats. So we have a FHIR repository that is optimized for serving out, for searching data in a large repository. And then you can also project it as SQL, which is nice for analytics. And this is a slide I stole from my venerable colleague, Pat Jameson, that shows a little bit. So the FHIR data there on the left is this JSON representation. It's got a lot of nested values. And you want to turn that into a nice, tidy table on the right. And you can see those two elements that you can just grab and specify within the FHIR SQL Builder very simply. You can put the ID in one column, and then you can dig way deep down into the JSON and get that, that other code down at the value, that's the value for the MRN, for the medical record number. And you want to make a column then in your data, you can rename it MRN. And that might be useful for other things. So the FHIR SQL Builder allows you to pick those things, decide what name of the column is, and only get the data that you really want. And you don't have to actually deal with all these other things that you're not particularly interested in, which is good for our machine learning use case because we were really interested in the codes and the lab values, and those are the things that were most predictive of the patient's health, at least for the population health measures that we were looking at. So then on to the next step, when you're doing getting it into ML-ready format, we took those features, so in each of those individual tables, we pretty much just picked the last or the latest event. And we categorized the lab results as normal or abnormal, and we got those ranges from inside the Cynthia source code. So this is kind of an interesting thing, is that laboratories each have their own set of cutoffs, what's normal and abnormal. How they run the test is different between different laboratories, and that introduces a lot of complexity that has to be managed, and that's one of the things that a clinical data model writ large will help you do. in our case, we were able to get those lab values, those ranges from inside Cynthia, because that's how they generated the data. They know exactly how they're generating a lung cancer patient or a stroke patient and what lab values are indicative of those and other codes, and they encode that into the source code that we could just pull out of there. So then the other step is target patients. For those, you need to only look at the data before they got their condition, and also before the horizon, or the length of time that you're predicting out from the present. And so to kind of illustrate that, you can look at this down at the bottom. I had trouble organizing this slide. There's a lot on it. But you think of each of those diamonds as clinical events. And then the one at the right there is a T condition. That's the time when someone's diagnosed with either a stroke or lung cancer in our case. But we parameterize this pipeline so that you could easily just plug in another code or another condition and develop the whole data set from that. So the horizon is this time from that time of the condition to some bit back. Before that. Could be a number of months, or it could be 1 month or days. What you don't want to do is include all of that data, because at the end, right around, okay, so what I found for stroke, and this is very common type of thing, if you're suspected stroke or you're having a stroke, you're going to get an echocardiogram. And when you then do machine learning and have the machine learning try to figure out what is it that predicts the stroke, it's going to pick echocardiogram all the time, because that's basically what happens in every event. So by using this horizon, you gray out, or we just ignore all that data that happens to the patient in the time leading up to their condition. That makes the machine learning model actually useful. Otherwise, it's just going to cheat and won't be very helpful. So the other set of patients are just background patients. And those you just get as much data as you can, and you want to have a pretty as balanced a data set as you can between the background patients and the target patients. This brings up another issue with healthcare machine learning, is class imbalance. There's almost always very few patients that actually have the condition that you're interested in, and then you have all these other people that kind of have a lot of data, and it tends to overwhelm the machine learning. So you have to do various things to try to balance that out, and there's no silver bullet to that. So then after you've categorized your patients, you figured out what data you're going to use and not use based on the horizon, then you can just simply pivot those and join them together. That's something in InterSystems Iris SQL. There is no pivot function. So that's something that our tool DBT actually gets around by implementing it by other means. And we didn't have to implement that. It's just standard part of DBT. So then the final bit is the machine learning and in training and test sets. So we have actually some SQL code that comes up with a random percentage, and it's also got a seed so that that's reproducible. Every time you run this pipeline, it'll use the same seed, and if you want to get a different subset, you can change that seed for randomly shuffling the data. And then IntegratedML is just called as part of it. And IntegratedML, just to back up, is all SQL machine learning in your database. And it really is just to help improve the productivity of data analysts, people that really know the data, don't want to install a whole other machine learning environment, learn another language. They just can work right in the data that they're comfortable with. And it just introduces these very simple commands: create model, train model, and then you have a predict function that you can use to get the values back. And so as far as results go, I mean, we'll look at it later, but this is the kind of curve as far as an ROC curve, which just shows the kind of the lift, the ability to do better than chance. So that dotted line is just randomly guessing, And then anything that's above that, any kind of curve above that is better than chance. And this is on par with essentially how the results they got in the paper for the number of patients that we did. So we're able to really reproduce their results for the most part. Okay, so let's see. So then I'll just kind of recap. These are all those steps, the whole pipeline all set up. And then how did we build it? Okay, so this is the tech stack, and I want to point out that this whole thing is open source. You can see all the mistakes we made. You can pull request, please, anything that you want to change. That's the one in the lower right. It's a QR code for our repository. And then this is built on a community-supported adapter for DBT to Iris that is developed by Dmitry. And within that repository that builds us up, we stand up a Jupyter notebook, we stand up the Iris for Health server, the repository. We have a Docker container that easily runs Cynthia and generates the data. And then we also stand up a superset server. That's a business intelligence open source project that we also have an adapter for. And really the way DBT fits into this, it's really kind of outside of the server. I mean, it's part of the repository, but it reads from and writes back to Iris. So it's really part of a new kind of way of doing analytics. It's kind of the data warehouse era now. Instead of doing extract, transform, and load, where you have to do a bunch of transformations on the data just to load it into your data warehouse, you now do extract, load, and transform. You land your data inside of the data warehouse in raw format, and then focus on transforming it from that raw format successively into more and more analytics-ready or machine learning-ready formats. And so DBT terms themselves as the T in ELT, all focused on the transform, focused on just going over that data that's in the data warehouse and transforming it into better and better data along the way. And so it's open source. It's mostly SQL-based, but they do have a way that you can write some steps in Python. It's a workflow orchestration tool. It manages the dependencies between all these different steps, which Dmitry will show you. And the other great thing is it's a very large community. It's like 50,000 people in their Slack channel. And it's really taking over as far as from Spark, where most data engineers, when they had a very large kind of pipeline to build, they would often use Spark. Now they're using DBT. And a little bit about how it works. It's really, you write SQL. As you can see, this is SQL, but it has macros and templates in it so that you can just use the overall concept of SQL as a select and group by, but then you can make it more powerful by introducing these macros that get expanded and allow you to write loops in SQL, which is not something you can do usually, and also make variables. So if you have, in our case, we ended up having a table with about 800 columns, each column being one of these medical codes, a LOINC code or a SNOMED code. We can just refer to subsets of those columns or the whole set of columns with one variable. You don't really write that in SQL. You just refer to it and build up your code that way. So it's a very productive way to write SQL and to write these kinds of these pipelines, and we'll see a little bit of that. So I think I'll switch now to demo and let Dmitry show a little bit about how this project works. And while I wondered if there's any questions now, if anyone has anything. We'll of course have time for Q&A later, but yes. Yeah, I uploaded already. Oh yeah, so he asked if the slides were already available, and or the slides will be available. I uploaded a previous version to the app, so it should be in there, but I will update it, and of course I can send you those. So yeah.
And it will be recorded, so after summit it will be available as a video. So to the demo. I'll give a brief introduction to DBT project, to the settings before I run it. So we have variables. We pre-configured few things like, yeah, we already prepared for the stroke prediction and lung cancer. And I can set up the target, which disease we going to predict, because it requires different data sets for the codes and some other things. And a few other variables we use for it. So I'll run dbt. It's a CLI tool. I do dbt build, and I put here change it variable, so I can change it in CLI. I don't need to change all this project file, and I'll exclude train table and below, because train takes some time, so we don't have so much time today. And I run it, and during run I will show how it's actually working. So the run will take like a few minutes, and you see here that it have 29 steps. It's quite a big project, small probably, yeah. But so it can run in parallel all the work, and for the first step it load seeds. So the seeds in dbt is just a CSV files with some static data which we need to use, and we put it in a special folder named scene, and dbt look for them and just load them. And yeah, we can define some more parameters to the seeds, and redefine column types, added alias, even add indexes to them for our SQL use, so it will be better in performance. So first of all, it ran in parallel all seeds, because it knows that they are not related to anything. And then we have one table which used as dependency for other tables. And again, it ran a few other transformation which can be run in parallel due to this dependency tree. So by now, it mostly ran our last representation. So it took last values in target period of patients by code. So we just filter a lot of irrelevant data. And by each run, it creates completely new table with all the data gathered from tables created by FHIR SQL Builder, actually. Yes. So go to the project. We have many files here, and in models, we defined a list of sources. So source is tables created by FHIR SQL Builder, which we use then in our dbt project. We have to define it. We even can define some tests. So it will be run against our tables, and it executes some tests already like this during the build. We have some more tables also with defined tests and so on. And even I excluded train model, but for instance, it materialized not to table, just we create a ML model in this. And with the power of dbt, we can do it. Let's back a bit to SQL files. So as already Tom mentioned, table observation. Let's me find where is it. Yeah, it's viewed by observation. So, for instance, observation table have a lot of data, some laboratory results, and we have to collect them and normalize it. But here we have just quite small SQL query, but with power of templating, we can do for loop over codes of values and call in terms of DBT is a macroses, but it's like a function in programming languages. So we normalize laboratory references. It's works on our seed with laboratory references, which can be easily edited, or we have additional hard-coded kind of list of macroses for few codes, which can be used in this case as well. So you see it's a quite short SQL query, but when DBT run it, it has to compile it to the SQL which will work on a database in IRIS in our case. So we have a hidden folder target and compile it, and all the compiled files will appear here. So we need to go to pivot, the same file by observation, and you see here those few lines of code created like a lot of very big, like once, 13 hundreds of lines of code. And you see like, a lot of transformation happening here because we need to make separate columns for each code. And yeah, for that we have this big table. Let's see what's happening here. So we already have 23 of 29. Most of first tables already done. So yeah, this by observation actually is the biggest one, as you imagine, and it will take most of the time. But as it's stable already, and we even already can look at the table. Like, let's have a look here. Select from, and here we are. Yeah, we have some ones, mostly nulls. Yeah, it's normalized for ML, so we need just few values like 1, 0, null, normal, abnormal for laboratory results and so on. And yeah, so and I can let's check what's happening. And already mentioned superset. We have prepared a dashboard which runs. So in this case, it shows on another run. It's for stroke database, stroke disease. So we can use superset to visualize data, even filter. Works quite good, actually. Yeah. Are you going to show a lineage by yourself? Or?
Yeah, you can do that. Yeah,
so DBT can generate documentation by models, what we have, and like it shows what we have in project. All details it created, like original. This one, I think let's by observation or pivot by condition. So yeah, all columns it generated and original code, and also interesting visualization as a graph. I think it's filtered. Let's filter it. So yeah, it displays all the connections between models, and we can see. Yeah, summary is our like latest table where we collect all. We then merge all resources in one big table, so it's like already ML ready. Yeah, it's already done. It's like 8 minutes. A bit more, and we can run this query. Yes, lung cancer. Let's have a look. Yes, so we have patient and all coded. So we for ML already for ML we don't need real names like what is this. We just have only codes and all the like normalized values in it. So yeah.
Cool. All right, yeah, switch it.
To
So yeah, so really just, this is kind of things that are cool about DBT. We mentioned tests, so it makes it really easy to kind of verify that you have one column for one thing and not another, and you can put those tests all over the place to make sure that your pipeline's running correctly. Talked about the parallel execution, dependency management, it's logging all the time. This SQL generation is really incredible. And it's just super flexible. Like we said, you saw in that parameter file, in the project file, it's a very simple thing to set up a whole new target. You just tell it which codes have to be there. It could be any of the diseases that are pretty much in the database, and you could rerun the pipeline, and it'll develop a model just for that. So I think it's a good tool for exploring what could be related to what. It wouldn't necessarily have to be diseases or conditions. You could look at any kind of data that way. And having the machine learning right in it makes it really, really powerful. I did want to mention, there's just some differences between the paper that I said and what we've done. We've gotten up to 30,000 patients that we've processed. We haven't gone higher. We're really focusing on getting the pipeline together. Of course, we're starting from our FHIR data, whereas the paper started from CSV. They did a little more extensive feature extraction. They actually did a mean over recent lab values, whereas we're just taking the most recent one. And they did a little bit different balancing of the data than we did. So that's pretty much presentation. I think I wanted to show that we've been using some new tools, DBT and Superset. We're supporting connecting those tools to Iris and making that a really good experience. New way of building ML. We've got automated feature engineering throughout this. And then even within the machine learning that happens, there's more feature engineering that happens underneath. And then really we're composing applications, keeping all the data in the database, and making it very reproducible, which is what's critical for any kind of analytics work. So with that, I think I'll conclude. There's definitely a lot of other FHIR sessions going on, so I encourage you to look through the program and pick some things out. So I think we can go to Q&A if anyone has any questions. Well, I know I'm a very clear speaker, but oh, there we go. Cool. Uh-oh.
Okay.
Uh-oh. No, don't give it to him. Oh, shoot.
No, this isn't that hard. I was just wondering, is there any cost to DBT? Or is this
No.
entirely?
So they do have a company kind of that provides a hosted service, but it's very much open source, and it's got a lot of community support for the open source side of things.
By the way, I didn't mention that we have, for this particular demo, we have around 45,000 patients, so it's kind of like a big data set for testing, yeah, and it's working quite fast.
Yeah, so my question is, what version of HealthShare do we need to use this?
So this is not HealthShare. This is Iris data platform. And so IntegratedML is not supported within HealthShare. Okay. So typically what you would do is you would set up an asynchronous mirror. I mean, HealthShare is such a beast, and it's usually serving patients in real care situations. You don't want to necessarily have a sandbox and be messing with that installation. So we have a very simple way to set up an Iris database next to it that's continuously updated, read-only, and then you can perform all this on that instance.
Okay.
And the version?
The version. The
Oh, version. Well, IntegratedML, I mean, for all of these things, just recent versions of InterSystems Iris. IntegratedML has been in it since 2020.1.
Yeah, so we are planning to upgrade to 2022. So
It'll be,
it
I
will
mean,
be
any version of Iris. And in fact, like if you have HealthShare, you can, even whatever version it is, you can set up a sandbox of a newer version of Iris next to it. They all work together. There's very little constraints between setting up an asynchronous mirror or an ECP node and what version you have on the source system. Sorry
Thank you.
about that. Sorry. Didn't quite get it.
Few more questions from Patrick.
Oh, excellent.
Just one other comment. The FHIR SQL Builder is relatively new, and so that's in 2023.1. So you got to keep that in mind. And it only works on the Iris for Health FHIR repository, not on the HealthShare repository.
Thanks.
As I have the microphone, I have a question for you. About terminology, you are mixing two terminologies. Was it an issue?
Mixing what?
Two terminologies. You are mixing SNOMED and LONIC.
Summit and I'm
SNOMED,
SNOMED and
and LONIC. That's two terminologies, and you can have an issue with that.
No, really it was, I think within Cynthia they just generate the appropriate codes and then they have, you know, for whatever it is. So with SNOMED, it's procedures and then LOINC is just the laboratory stuff. So they end up being in different tables anyways and you just want to manage everything together as appropriate. No issue. All right. Excellent. Oh.
So this was very impressive. I'm wondering, is this mainly about developing the tool in order to discover these rules? Because what you just taught it was the assumptions you made in your Cynthia data, right?
Well, I had a paper to start with, right? And I'm really just kind of recreating what they did to some extent, just to prove that this was possible. One of the things that they did, and this is what I'm going to look at next, is that they you know, after they developed these models, they ranked the features by how important they were to the model. We actually, which is a subset of like, you know, 80 codes versus the 800 that we have essentially in our big table. I tried to build a model with just the codes that they found most informative, and it didn't perform well at all. So there's definitely something different between the way their model works and the way ours works underneath. So I'll get into that a little bit. That's something that IntegratedML doesn't have as a feature right now, to actually just spit out your feature importance and do this kind of explainability. But you know, there's a lot of different ways to do that. So it's a feature that's coming. But thanks, yeah.
How many hours did you put in this project?
How many hours? How many hours?
How many hours for?
For Dmitry did all the coding.
Yeah. Yeah, it took a while. I can't count how much time I spent.
So we started in what, January essentially, February?
Yeah, it was like two-part project. We implemented DBT first, then started working on particularly on machine learning. Machine learning part was in April. We started in April.
Yeah, April, pretty much. So, I don't have an idea of how long it took, but really the hardest part was starting out, figuring out all the lab cutoffs and how to do that, I believe, right?
Yeah.
And once that was done, it was really just a matter of kind of finishing it up.
So if you had to do something very similar, how long would it take? So,
Yeah, because he was
day-
learning the tool.
Right.
Didn't even know DBT.
Right. So So now that you've gone through that learning curve, what would similar parameters, different stuff?
To do the same, so add new target to the prediction, it will take, let me
I think the question is more, correct me if I'm wrong, something, maybe it's a logistics data set or something like that. Similar complexity, totally different data, totally different things to figure out, but now you know the tool, so now...
Now I know the tool, I can do it, pretty fast, because with the help of DBT, for this particular project, most of time I spend doing this normalization thing, how to normalize laboratory results, find what normal, what abnormal, collect it, because I have first iteration of normalization in the macros. It will be where is my macros? It will be, right here. I created this quite big macros file. It's generated mostly from Synthea, because I not working with health, I have no idea what, I don't have medical background, but I needed to make some proof of concept that we can normalize it. So I spent a lot of time on just finding how to automate this part. Then I came to another idea and made just a CSV file, which in fact I mostly asked it from ChatGPT for these values. I now managed to get the CSV file, quite small macros, which reads these values and converts to SQL, and it became even faster. So yes, a week at top, I think, for any new project, kind of like this. So yeah.
The price is going down.
Yeah.
Due to all that.
And just to clarify, when you say normalizing the data, are you just mapping the values of the range to something a little bit more compact, like 0 to 1? Is that what the main task is? Or I guess I'm not too familiar with
that. It's just you have a value that you see, and you have to decide whether that's normal or abnormal type of thing. So you have to compare it to some reference ranges. And so figuring out what those ranges are, what the cutoffs are, is important and is not explicitly stated anywhere within Cynthia. It's just kind of encoded within their modules.
Yeah, here, I have another macros helper. So I have collect data, value quantity, value unit, and check that it's in this reference, and say if it's fit in, it's in references, it's normal. If not, abnormal. So very simple.
Okay. Any more? All right. Thanks for the great questions. Excellent, and thanks for your attention.